It's pretty wild to think that Albert Einstein, the guy who completely reshaped our understanding of the universe, spent the last 30 years of his life fighting against a theory he actually helped create. That theory was quantum mechanics. Now, he didn't think it was wrong exactly, but he was absolutely convinced that it was incomplete. So let's dive into this epic intellectual battle, Einstein's hunt for a complete reality he believed was hiding behind the spookiness of the quantum world.
This one sentence, right here, just perfectly captures Einstein's whole problem with it. For him, the universe had to be orderly, predictable. The very idea that the most fundamental level reality was just a cosmic game of chance, well, that was something he could just never get on board with. And look, this wasn't some dry academic disagreement. This was a deep philosophical belief that kicked off one of the greatest debates in the entire history of science.
So, what on earth did Einstein mean when he said quantum mechanics was incomplete? He wasn't just trying to be difficult, I promise. He was basically saying any good theory of the universe has to pass two tests. First, do its predictions actually work? And second, does it give you the whole story, a complete description of reality? For Einstein, quantum mechanics might have passed the first test, but it was failing that second one big time.
Okay, so this slide really gets to the heart of the clash. On one side, you've got Einstein's gut feeling, what we call local realism. It basically says that a thing, like the moon, has definite properties. It has a position, a speed, whether we're looking at it or not. And crucially, nothing can travel faster than light. That's locality. Then on the other side, you have the standard quantum view, which says, nope, a particle's properties are just a cloud of probabilities until you actually measure them. The very act of looking defines reality. It's a fundamental disagreement about how the universe even works. So Einstein wasn't just going to sit back and complain. No, he decided to formalize his challenge. He teamed up with two other physicists, Boris Podolsky and Nathan Rosen, and in 1935, they dropped a bombshell paper, what we now call the EPR paper. It was designed as a kind of logical trap, using the weirdest parts of quantum mechanics against itself to prove that there had to be some hidden information the theory was missing.
And here it is, the money quote, straight from the paper itself. Their conclusion was simple. The wave function, this core mathematical tool of quantum mechanics, just doesn't tell the whole story. They were convinced that underneath all that quantum weirdness and probability, there was a deeper, more solid reality that the theory just couldn't see. The whole basis for their argument, the real linchpin, was a phenomenon so bizarre, so completely counterintuitive, that Einstein himself gave it its famous nickname, spooky action at a distance. And this, folks, is where things get really, really weird. That spooky action is what we now call quantum entanglement. Now try to wrap your head around this. You can have two particles that are linked, connected. They could be on opposite sides of the galaxy, and yet they behave as a single unified system. What you do to one of them instantly, and I mean instantly, affects the other. It's this instantaneous connection that just shatters all of our everyday rules about space and time.
So the EPR paper laid out this brilliant thought experiment. It goes like this. You create two entangled particles, maybe with opposite spins. You then send them flying apart in opposite directions. Now, if you measure particle A and find its spin is up, quantum mechanics tells you that you instantly know particle B's spin must be down. For Einstein, this was the smoking gun. How could particle B know what happened to particle A faster than light could travel between them? His answer was simple. It didn't. The information, the spin-down property, was there all along, hidden from our quantum description.
For decades, this was basically a philosophical standoff. It was Einstein's powerful common-sense intuition versus the bizarre but incredibly successful predictions of quantum theory. There was just no way to know who was right. Until, that is, a brilliant physicist figured out how to drag this whole debate out of the ivory tower and into the real world.
And, really think about that. How in the world do you build a machine to test two competing versions of reality itself? It honestly seemed impossible, but physics has a way of surprising us. The breakthrough came from this absolute genius, an Irish physicist named John Bell. In 1964, Bell did something incredible. He took Einstein's philosophical argument and turned it into a hard, mathematical prediction that you could actually test in a lab. He found a way to literally ask the universe to cast the deciding vote. And this is the magic of Bell's theorem. He basically said, okay, let's stop arguing and let's measure something. He proved that if Einstein is right, if the world is based on local realism, then the correlations between measurements on entangled particles can't be stronger than a certain value. It's like a cosmic speed limit. But
And this is the kicker, quantum mechanics predicted the correlations would be stronger than that limit. It predicted they would break Einstein's rules. All of a sudden, philosophy became a question you could answer with an experiment.
So the stage was set for one of the most profound experiments in the history of science. The question was finally put to the universe: are you the classical, local, sensible place Einstein believed in, or are you quantum, connected, and, well, spooky?
The first definitive answer started rolling in during the early 1980s from a series of game-changing experiments led by the French physicist Alain Aspect and his team. They literally built a machine to settle the debate, a device that could create entangled particles and measure them with incredible speed and precision.
And here's what they found. It's pretty mind-blowing. That bar on the left, that's the absolute limit, the maximum correlation you could ever get in Einstein's local realist universe. The middle bar is what quantum mechanics predicted they'd find, and that bar on the right, that's what their experiment actually measured, again and again.
The verdict was in, and it was completely unambiguous. The experimental results smashed right through Bell's limit. The correlations between those distant particles were stronger than any classical local theory could possibly explain. The universe had spoken, and it sided with quantum mechanics.
The implication of this is just staggering. It means our universe is fundamentally non-local. That spooky action at a distance that bothered Einstein so much isn't a flaw in the theory. It's a real, confirmed feature of our reality. Two particles can be separated by galaxies and still be part of one single, interconnected system.
And this wasn't just a one-time fluke. Oh no. As you can see here, since Aspect's pioneering work, these experiments have been repeated with more and more precision. By 2015, several teams had performed what they call loophole-free tests, closing every possible escape hatch for a classical explanation. The case is pretty much closed, folks. Our world is officially quantum spooky.
Okay, so Einstein was wrong about local realism. Case closed, right? Well, not exactly. Because what about his other big worry? That deep-seated feeling that quantum mechanics was still incomplete. That question is very much alive, and it's leading physicists to some truly fascinating new ideas about reality. You see, even in being proven wrong on this point, Einstein ended up being incredibly productive. His relentless questioning, asking what a measurement really is and why this cloud of probabilities suddenly collapses into one definite answer, has pushed generations of physicists to search for a more complete picture.
One of the most exciting paths forward is this family of ideas called objective collapse theories. And the core idea is pretty radical. What if the wave function collapse isn't some magic trick that happens only when we look at something? What if it's a real physical process that happens all on its own, baked into the laws of nature?
A top contender here is something called the CSL model. The idea is that every particle in the universe is constantly getting hit with these tiny, random localization events. For just one particle, it's almost unnoticeable. But for a big object with trillions of particles, all those tiny hits add up and basically force it to be in one definite place, just like the chairs and tables we see every day. And the coolest part? This makes a testable prediction. It suggests there's a new kind of background hum or heating in the universe that incredibly sensitive experiments are now being built to look for.
And this brings us right back to the heart of Einstein's quest. The experiments have shown us that reality is undeniably spooky and interconnected, but they haven't told us if that underlying randomness is the final word, or if ideas like CSL are pointing us toward a deeper, non-local, and maybe even a more complete reality we just haven't uncovered yet. The search that Einstein started, well, it's far from over.